Today is Sunday, 15th of June 2025, 6 a.m. Eastern Time. This news is brought to you by Preeti Capital.
Okay, let's unpack this. Quantum computing. I mean, the promise is huge, right?
Absolutely huge.
Tackling problems we can't even dream of solving now. Uh, Changing everything from medicine to material science.
For sure.
But if you follow the space even a little, there's this massive, persistent hurdle.
Oh, yeah. The errors.
These qubits, the building blocks, they're just incredibly unstable. They lose their quantum state so easily because of, noise from the environment.
hmm
It really is like trying to hold a thought in a room full of shouting people.
That instability, that's the Achilles heel. We call it decoherence.
Decoherence, right?
And even the, slightest interaction with anything around it can just corrupt the quantum information, scramble your whole calculation before it's even done.
So building these big, reliable quantum computers
Mhm.
really hinges on getting past this.
Critically dependent on it. Yeah.
Exactly. And, while loads of brilliant people are working on complex error correction stuff,
Right, the algorithms, the extra qubits.
yeah, often needing tons of extra physical qubits just to protect one logical one.
Yeah.
Sometimes hundreds, maybe even thousands, they say.
It's a huge overhead.
But we've got this stack of sources here, and they're highlighting a really different path, something Microsoft is chasing.
Mm-hmm.
They're not just focusing on correcting the errors after they happen. They're trying to build a qubit that's, inherently tougher, more robust from the start.
Yeah, it's a fundamental difference in approach.
They're chasing something pretty wild, straight out of theoretical physics.
Yeah.
Majorana fermions.
It's a fascinating pivot, really. Instead of adding all these layers of software and extra hardware after the fact,
Right.
this approach aims to engineer the actual fundamental particle, or quasi-particle in this case, to be less bothered by the noise in the first place.
Okay, so that's our mission today. We're going to really dig into these sources. We need to figure out what these Majorana fermions actually are,
Yep.
why their weird properties might be revolutionary for this whole quantum error problem,
Right.
and what Microsoft is actually doing in the lab trying to make them real.
How they're trying to harness them.
Yeah. So get ready for some insights into what could be a kind of shortcut to building more stable, fault-tolerant quantum computers.
It's definitely not just about different hardware. It's like leveraging a whole different kind of physics for computing. Pretty cool stuff.
All right, so where did this whole idea even start? Our sources mention a physicist from, way back.
Yeah, the concept itself goes back to Ettore Majorana. He was an Italian theoretical physicist.
Okay.
Proposed their existence way back in 1937. He was kind of an enigmatic figure himself, actually.
Interesting. And what was the core idea, the sort of mind-bending property he thought these particles would have?
The really unique thing, and the reason they're so interesting for quantum computing, is that they are theorized to be their own antiparticles.
Their own antiparticles. What does that even mean?
Well, think about, electrons and positrons, right? They're a particle-antiparticle pair. They annihilate each other. A Majorana fermion is theoretically its own opposite. It's a fermion. It's charge neutral. And in a way, it's its own mirror image. It doesn't need a separate partner.
Wow. Okay, so they're these weird self-paired particles. But how does that specific property help with quantum computing? How does it tackle the error problem?
So this is where it gets into what's called topological quantum computing. That's the framework Microsoft is really betting on here.
Topological, okay.
And it's not about using the Majorana itself as the whole qubit necessarily. It's about using them as key components. Specifically, they're predicted to behave as something called non-abelian anyons under very specific conditions in material.
Whoa, okay. Non-abelian anyons. That sounds complicated. Can you break that down a bit? What does that mean for a qubit?
Right, it does sound complex, but in simple terms, it means if you have a few of these things in a system.
These non-abelian anyons.
Yeah, based on the Majoranas, if you move them around each other, they call this process braiding.
Braiding, like braiding hair.
Sort of analogous, yeah. The final state of the whole system depends on the order you move them in. The sequence of the braiding matters. It's like the particles, or rather, the system, remembers the path they took relative to each other.
Okay.
And this memory, the information, it isn't stored in the local state of just one particle. It's stored in the topology of that braiding pattern.
Okay, wait. So the quantum information isn't just sitting there on one tiny fragile spot.
Exactly.
It's somehow spread out, encoded in the pattern of how these Majoranas are moved around or interact.
Precisely that. The sources really emphasize this. The information is stored non-locally. It's distributed across the system, encoded in the properties of these Majorana zero modes, which appear at the ends of special wires.
The local storage.
And that makes the quantum information inherently robust. Think about tying a knot in a piece of string.
Yep.
The knotness isn't in any single point on the string, right? It's
Yeah.
in the overall structure, the topology. You could wiggle the string, push it around a bit.
And the knot stays a knot?
Exactly. The knot remains the same unless you do something drastic like cut the string or deliberately untie it. Local jiggles don't destroy it.
Got it. So these Majoranas, appearing as these special non-abelian enons that you can braid, let you store quantum info in a way that's protected by this topology,
Yes.
making it naturally resistant to local bumps and noise from the environment.
That's the core idea. That topological protection offers a kind of natural defense against the decoherence and noise that would just instantly kill a regular qubit state.
So it could massively reduce the need for all that complex error correction software and the huge number of extra qubits.
That's the hope. It significantly cuts down on the need for that massive overhead of redundant qubits that other approaches rely on for software-based error correction.
So that's the potential shortcut we mentioned. You might need far fewer physical bits to get one reliable, fault-tolerant logical qubit.
Potentially, yes. If it works reliably. That's the big if.
Okay, so the theory sounds amazing. Powerful stuff. But how does Microsoft actually plan to, create these things and control them? Where do they even look for Majoranas in the real world?
Right, because they don't just float around freely. They're pursuing them as what are called quasi-particles.
Quasiparticles.
Yeah, like particle-like behaviors that emerge from the collective interactions of electrons within certain exotic states of matter. Specifically, the sources say they're focusing on topological superconductors.
Topological superconductors.
Yes, okay.
And the actual setup, it involves special materials, really specific conditions.
Exactly. The kind of standard setup Microsoft has been pushing, described in the sources, uses these hybrid systems. They combine superconducting materials with certain types of semiconductor nanowires.
Nanowires. Tiny wire.
Really tiny. They mention materials like indium arsenide nanowires.
And you just stick them together.
Well, you bring the nanowire into really close, pristine contact with the superconductor. Then you apply specific magnetic fields, and you have to cool the whole thing down to incredibly low temperatures.
How low?
Cryogenic. We're talking fractions of a degree above absolute zero. Really, really cold.
Okay.
Under those very precise conditions, the theory goes, the interaction between the superconductor and the semiconductor can create this special topological phase within the nanowire.
And that's where the Majoranas pop up.
That's the prediction. Theory says that within this phase, you should get these zero-energy Majorana states, often called Majorana zero modes, appearing, and they should be localized right at the ends of the nanowire segments.
At the ends. Okay.
And those are the non-abelian enons they want to manipulate.
So you've got these super cold nanowires, Majoranas maybe sitting at the ends. How do you actually compute with that? How do you do the braiding?
Yeah, that's the tricky part. Physically dragging these modes around is incredibly difficult. So the sources talk about using electronic gates, basically, applying voltages or fiddling with magnetic fields very precisely nearby.
To nudge them.
Effectively, yes. To control their interactions or change their apparent positions relative to each other on a chip. By carefully orchestrating these changes, moving or swapping the positions of these Majorana zero modes, you perform the braid operation electronically.
Oh, okay.
And the result of that sequence of braids gives you the answer to your quantum computation. And crucially, because the info is locked in that topological property of the braid,
It should be much less sensitive to little errors in the control signals compared to trying to delicately control a standard qubit.
exactly, much more resistant to noise during the operation itself.
Wow. That still sounds like an incredible engineering challenge to get right consistently.
Oh, it absolutely is. You need unbelievably pure materials, perfect interfaces between the superconductor and semiconductor, extreme cooling, and nanoscale precision in controlling those electric and magnetic fields.
And just finding them,
Yeah.
proving they're there.
That's been the huge experimental frontier for years. Detecting these modes, confirming they are Majorana zero modes, and showing they have the right non-abelian properties needed for this robust computation.
The sources do point out that while lots of groups have been searching for Majoranas in materials for a while,
Yes, it's a hot area of research globally.
Microsoft has been making specific claims about progress, about actually detecting and manipulating them towards this goal.
That's a key point. Their focus has really been on building the specific hardware platforms, these hybrid systems that could host and control these states, and then running the experiments to measure signatures consistent with these non-abelian Majoranas needed for the braiding and protection.
It definitely sounds like, as the sources say, a significant departure from the more common approaches. They're really pushing into uncharted territory.
They really are. It shows a big commitment to this unique path.
So wrapping that section up, the potential for built-in error resistance is massive, but actually making it work reliably, creating, finding, confirming, and controlling these Majoranas and their braiding, that remains the core challenge they're working on.
Precisely. It's definitely a high-risk, high-reward kind of venture.
Which brings us neatly to the so what question.
Hmm.
Why should you, listening right now, care about Microsoft chasing these theoretical things in super cold nanowires?
Well, because this whole effort is a major bet. It's a bet on one specific way to potentially leapfrog the biggest obstacle we have in quantum computing today, the error problem.
Right.
If they succeed, if this topological approach using Majoranas actually pans out, it could mean a path to building truly scalable, fault-tolerant quantum computers much sooner, or maybe with way less hardware complexity.
Than the approaches that need mountains of extra qubits just for error correction.
Exactly. Compared to methods relying solely on those traditional error correction schemes that demand huge redundancy.
And the potential impact, as the sources list, is enormous, solving currently impossible computational problems.
Yeah, things in chemistry, materials.
Major breakthroughs in cryptography, both breaking current codes and creating new ones.
That's a big one.
Revolutionizing drug discovery, simulating complex systems like climate or finance. The list goes on.
Right. Those huge potential applications are the ultimate goal, the destination. And Microsoft sees Majoranas as a potentially more direct route to getting there because they tackle the error problem right at the hardware level.
It's a really pivotal effort in this whole global race for practical quantum computing.
Absolutely. And if they can truly demonstrate robust topological qubits based on these Majoranas, it could genuinely redefine the entire landscape.
So understanding this specific, quite unique approach that Microsoft is pursuing gives you, a window into one of the absolute cutting edges of technology and physics. It really highlights how researchers aren't just trying to optimize existing ideas, but sometimes they're digging deep into fundamental physics to find completely new ways to compute and get around massive roadblocks.
It really is a testament to exploring fundamentally different paths when faced with really tough scientific challenges.
So, to sort of wrap it all up, Microsoft is making this significant high-stakes bet on chasing Majorana fermions. These particles, theorized to be their own antiparticles,
Right.
could, if harnessed correctly in these special materials, enable a topological form of quantum computing.
Which offers this powerful built-in error resistance.
Exactly. Potentially speeding up the timeline for getting truly useful, scalable, fault-tolerant quantum computers by drastically reducing the need for those complex error correction layers that bog down other approaches.
It's really about leveraging deep, almost esoteric theoretical physics to try and sidestep some very practical, very difficult engineering hurdles that plague other methods.
Okay, so here's a final thought for you to mull over, something to consider. If this topological approach, using Majorana fermions, really does offer such unique error resistance compared to methods needing heavy error correction, how might the success of this specific path change the kinds of problems quantum computers tackle first? Or how might it shift the whole timeline for when we achieve truly fault-tolerant quantum computation? Something to think about.